Good day, students. I am Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dungar College, Bikaner. Today, I am going to deliver a lecture on superconductivity, which is a topic of MSc Final Physics. In my previous lectures, I have discussed what are superconductors, Misner effect, London equations. So I am going to initially first give you the brief description of what I taught in my previous lectures. What are superconductors? Superconductors are the materials which possess zero resistivity, that means infinite conductivity. Superconductivity is a temperature dependent phenomena. Below a definite temperature known as transition temperature or critical temperature, material will be superconductor, and above that temperature, material will behave as normal material. It is not necessary that all materials are superconductors. There are some specific materials which show the phenomena of superconductivity. We have also dealt with Misner effect. What is that effect? Misner effect shows that when a superconducting material is placed in a magnetic field, it is found that magnetic field lines do not penetrate inside the superconductor. That means inside the superconductor, B equal to 0. This is true for simply connected superconductor, for example, sphere, and it is also true for multiply connected superconductor, for example, ring. We have also derived London equation. The London equation is based on two fluid model, and in that we have shown that inside a superconductor, when it is placed, when on the surface we apply a magnetic field inside the superconductor, the magnetic field will decay exponentially. And we have determined London penetration depth. The value of London penetration depth is found to be very small. Now we will deal with thermal properties of superconductor. Thermal properties means the properties which are dependent on temperature. These properties include entropy, specific heat. These are the properties which we will deal today. So my first thermal property is entropy. It has been found that in superconductors, entropy decreases when a temperature is lowered below critical temperature. This can be shown with the graph. This shows the variation of entropy with temperature. Here I have plotted entropy of superconductor, which is denoted as SS, and Sn denote the entropy if the material is in normal state. Here I have shown the critical temperature Tc. It is clearly evident from this graph that when temperature is below Tc, the entropy of superconductor decreases below the critical temperature. We already know that entropy is a measure of disorder. More entropy, more disorder. Hence, this decrease in entropy between the normal and superconducting state tells us that superconducting state is more ordered than the normal state. That means SS is less than Sn. This shows that superconducting state is more ordered than the normal state. Now What this concludes that some of the electrons, or we can say all of the electrons which are thermally excited in normal state become ordered in superconducting state. In superconductor, there is a spatial order which extends over a distance of order of 10 raised to power minus 6 meter. This range is called coherence length. Next property is specific heat. In the normal state, specific heat can be expressed as Cn is C electronic plus C phonon. What does the first term means? This is the specific heat of electrons in metals. And what does C phonon means? This contribution in the specific heat comes from lattice vibrations at low temperature. Specific heat is temperature dependent property. The electronic contribution varies with temperature linearly. That means electronic contribution is gamma T, and the contribution of phonons, that is lattice vibration, it varies as T cube. Removing the proportionality sign, we will get constant. So the phonon contribution will be equal to beta T cube. Gamma and beta are constants. Now, this is the specific heat of normal material. We have to deal with superconductors. Differentiating normal and superconductor, what will be the effect of contribution of specific heat, whether it will be electronic or phonon contribution? As we know that superconductivity affects electrons, hence the lattice vibration part will remain unaffected. That means it will have the same value beta T cube as in the normal state. Now we are left with the electronic contribution, which was initially for the normal material varies as linearly with temperature. So we have taken for normal metal C electronic to be equal to gamma T. Now for superconductor, it has been found that this contribution, electronic contribution, varies as an exponential form. That is, electronic contribution of superconductor can be expressed as A exponential minus delta upon kBT. What are these parameters? Here T is the temperature, C electronic means, as I've already stated, electronic contribution, A is constant, Kb is Boltzmann constant, and this delta, this is the energy gap of superconductor. Here I have shown the graph of electronic contribution of superconductor and normal material with temperature. Tc is the critical temperature. Initially, I am taking the temperature to be greater than Tc. That means material here is in the normal state. It is clear from the figure that this is the electronic contribution of normal state. But what happens at Tc? There is an abrupt jump at Tc in the electronic contribution of specific heat. And below the temperature Tc, the graph varies according to the curve. That means at T equal to Tc, there is discontinuity in the specific heat curve. I am saying this transition which is occurring at Tc to be second order transition. Why second order transition? The order of the transition is determined by Gibbs free energy. Since specific heat can be expressed as minus T del 2G upon del T square. So we have to do double differential of Gibbs free energy. This differential, the order of the differential determines the order of transition. Hence, this transition is a second order transition. So, we have seen two properties of superconductors. First was entropy. Entropy of superconductors decreases on cooling below the critical temperature. Similarly, I have shown that when there is a variation in electronic contribution of specific heat, there is an abrupt jump at T equal to Tc. Now we will deal with the third property of superconductors. This third property, thermal property, variation with temperature, is the thermal conductivity. Thermal conductivity is plotted on y-axis and on x-axis I am taking temperature. The thermal conductivity of superconductor undergo a continuous change between these two phases, and it is found that thermal conductivity in the superconducting state is lower than that in the normal state. This shows that electronic contribution drop and the superconducting electrons, they play no role in heat transfer. This shows the variation of thermal conductivity with temperature. These are the important properties which shows the variation of physical quantity with temperature, and most important is the point, that is Tc, which is termed as critical temperature or transition temperature, because the property is completely different above and below this temperature. Thank you students for watching.